So our first unit, first section in the quadratic unit for pre-calc is going to be a big review. So I'm going to go through a lot of the topics very quickly, and if you need a more thorough explanation of all the topics, then I would like you to go back to my Algebra 2 playlist and look up that topic in particular and get a more thorough lesson. But like I said, pre-calc, we're going to go kind of quickly through this. But these are very important topics to us. Now, in this particular worksheet of notes, the first two problems are just a review from the previous unit for this lesson. I think we'll just skip it for YouTube and move on to number 3, where it says quadratics that could be solved without the quadratic formula. Now, the quadratic formula, remember, is that baby, which we'll get to that in a second. Every quadratic can be solved with a quadratic formula, but that doesn't mean it's the most effective way to solve it. So the thing I noticed in number 3 is that there's only one term that has a variable component to it. So if I'm trying to solve a quadratic with just one variable component, an x squared term, I should probably think about square rooting. And I can't square root until the x squared is isolated. So we're going to add 5 to both sides, expand the screen a little. I get 3x squared equals 21, and it's best to wait to square root until the x squared is completely isolated, or at least the squared term is isolated. And then we end up with a square root step at the end here. And remember that when you're solving an equation and you go through and square root each side of the equation, the solution is not just the positive answer, but also the negative answer. So it is the square root plus and minus the square root of 7. I don't want decimals here. Algebraic answers, we generally want really pretty answers, so leave them like that. It is irrational. So here, the thing that's being squared is the entire term of x plus 2. So before I square root, we're going to want to isolate that. So let's add 10. Then back in Algebra 2, a lot of kids thought they should distribute that 3 into the x plus 2 squared term. That is a big boo-boo. Don't do that. Because it's not x plus 2. It's something totally different. It's a foiling question, essentially. So we have the quantity x plus 2 squared equals 25. And now would be the moment in our math where we square root both sides. So same rule applies here, that when you square root an equation in an effort to solve, you have both positive and negative answers after the square root component over here. So it's positive and negative, and this time instead of saying the square root of 25, we're going to call it the square root of 5. And then I'm still going to isolate for x. I'm going to solve for x, so I'm subtracting 2 over. So we have negative 2 plus and minus 5. Now I want you to take this further than that as your solution, because these are integers, which means we have nice answers that we can separate. So negative 2 plus 5 is 3, and negative 2 minus 5 is negative 7. So in both of these examples, we did end up with 2 answers. This one has positive 7 and negative 7. This one has negative 7, square root, sorry. This one has negative 7 and 3. Let's see what happens here. So the thing that's being squared is already isolated. Let's go ahead and square root both sides. And we end up with x minus 3. Oh, why'd you put parentheses? They're gone. We don't need the parentheses to group anything anymore because it's isolated now. So remember what we said about the solutions is not just positive square root of 5, it's also the negative square root of 5. So to isolate the x, our last step is to add 3 over. And in this case, because we're going to have irrational numbers, I don't want to truncate or round off any decimals. 3 plus square root of 5 is one of my answers, which is ugly if I were to write the decimal. And also 3 minus square root of 5, another very disgusting answer, but we're going to leave it like that. So those are my 2 solutions. I don't mind if you leave them grouped with 3 plus and minus square root of 5. But if we were trying to approximate with decimals and had to give real life answers, we would have to understand what those 2 answers mean and which ones were appropriate in a real life problem. We'll come back to you, quadratic formula. All right, my favorite method is completing the square. And the idea for completing the square is we're going to revamp the whole equation so that we can create a binomial squared, which allows us to take the square root, because we can all agree after sitting through Algebra 2 that square rooting is the easiest method for solving a quadratic. But the problem is not all of them are set up to square root. Like for instance here, there's 2 terms that have an x in them, so we can't just square root both sides. It wouldn't do us any good. But if we were able to rewrite it in a form where it was something squared equals a number, then I could square root. So the idea is move your constant to the right side of the equation, already there, and then you're going to leave a blank so that you can complete the square. But the issue with an equation is you have to keep it balanced. So if you add a blank to the left side, you also have to add it to the right side. So the issue is what goes in the blank? Well, let's find out. So the formula for the blank is half of your b term squared. So you take this middle coefficient, b, half of it, so in our case 3, and then square it, so we have a 9. And if I add 9 to the left, I have to also add 9 to the right. So what did that do? Well, let's look. X squared plus 6x plus 9, because I followed that formula, that is the same thing as the factorization of x plus 3 times x plus 3, better known as x plus 3 squared. And then over here, that's 16. Hey, look at that. I have something that I can square root. So okay, what's happening is we're rewriting it so that I can square root it, because I love square rooting. And then same as one of the previous problems where we are going to have integer answers. So please go far enough to actually give me the integers. -3 plus 4 is 1, and -3 minus 4 is -7. It's been a lot of 7s in my answers. It's weird. All right, so this next example, same idea. The constant is already on the right-hand side. So it's all set up to add the blanks. Your job is to figure out what goes in the blank. All right. So in the blank, half of this b term is -5. Then when I square it, it's a positive 25. And this trinomial is perfect, and it factors into x minus 5 times another x minus 5. What's that, 36? All right. Square rooting both sides. X minus 5 equals, don't forget, positive and negative. So take the answer far enough so you actually give me the two integers in this case. So x equals 11 or x equals -1. I love completing the square. Unfortunately, it's not always the best choice. So two things that you have to look for before you complete the square, like if you were given a choice of using any method you want, sometimes it's not the best choice. I'm not saying it's not doable, it's just not always the best. So the first thing we have to look for is make sure that this first coefficient of a is a 1. It is, that's good. The other thing I personally look for is the b term. I really prefer it to be even because I don't really enjoy fractions. But if I'm forced to do quadratic, completing the square on this quadratic, I could. So let's see what that looks like. I need to move the constant over first. So I'm going to, oops, that's a 13. I'm going to go ahead and leave a blank because I'm going to need to add something there to complete the square. But remember, we're going to need to move the constant over. So 4, and then whatever the blank is, I got to add it to both sides. So taking half of 13, think about that, guys. I know it's a decimal, just leave it as 13 halves for now. And then you're going to square it. Well, when you square a fraction, you just square the numerator and the denominator. So that's 169 over 4. Lovely. So what did that do? Well, the way this factoring pattern works is you don't have to think super hard about how it factors. It's always the x and then half of your b term. So half of your b term here would have been 13 halves. This is where it's like not very exciting. If I wanted to add these two fractions together, I would have to get common denominators, which means I'd have to think really hard about changing this to a 16 over 4, and then 16 plus 169, I'm cheating because I already did this problem, is 185. 185 over 4. I'll be honest, guys, if I was just doing this on my own, I would have typed that in my calculator and hit math enter because it's late and it's summer and I'm tired. Okay, so now I'm ready to square root both sides. And think about when you square root a fraction, what you're doing is you're square rooting the numerator and denominator separately. So this turns out to be the square plus and minus the square root of 185, which I gotta think about if that reduces or not, over 2, because the square root of 4 does reduce to a 2. And I'm referring to my cheat sheet of answer key here. Turns out that does not reduce as far as the square root of 185. You know, I tried dividing it by 4, 9, 16, and so on. But my final answer, a little gross, -13 halves plus and minus square root of 185 over 2. However, notice how they have the same denominator? You could just rewrite it as one solid fraction, that's a 13, plus and minus square root of 185, all of it over 2 as one common denominator. So we're going to have some fun later where we solve one quadratic multiple methods. This would have been a good one for quadratic formula. And my answer for completing the square and my answer for quadratic formula would have ended up being the same thing because guess what? They both work. So well, let's see. Factoring. Oh, love it. So my puzzle solvers really love factoring, and some of them are very challenging and some of them are not. Okay, comes with the territory. So remember, factoring is the reverse of FOILing. So you want to look for a common factor first. There's none. And then we want to reverse FOIL or undistribute, or however you want to think of it, x times x for the first parts. And then I want my last two terms to multiply to -9, and I want my outside inside to add up to -8. That was a pretty simple one, right? So that'd be a, I say that and then I mess it up, -9 and a +1. But we're solving these quadratics by factoring. So now you have to take your factors, and then each one has to take their turn to be 0, because either one of those factors could be 0 for this product to come out to 0 as a solution. So x equals 9 is one possible solution, and x equals -1 is another. Now, it's fun because in Algebra 2, when we first start learning about factoring, like really learning about factoring, even Algebra 1, some kids claim they absolutely hate it and they just can't wait for it to be gone. And then we find out, unfortunately, that it never went away. And we just kept going at it in Algebra 2. And then when we started doing some really like weird problems where you could choose to solve it however you wanted to, do you know what method most kids chose? Factoring. So go figure, right? Unfortunately, not every quadratic will factor, and that's kind of the obnoxious part. There are ways for you to tell if it's going to factor so you don't waste too much time, but most of us don't want to go through that effort. So here, my factors at the end need to multiply to -14, add up to +5, so they need opposite signs. Thinking a +7 and a -2. But when I solve those factors, I'm going to skip a step. This one produces a solution of -7, and this one produces a solution of 2. This one's fun. It's like my favorite factoring pattern because I notice there's no middle term, which indicates that my last terms are opposites of each other, additive inverses we call them. So I would be thrilled if my teacher just gave me a bunch of these questions, but you know, she wouldn't be that nice. So how about +7 and -7? That would work, right? So my solutions, haha, end up being x equals -7 and x equals +7. If you ever see solutions written like this in set notation, totally okay. They do that a lot on the ACT test, and I'm not sure about the SAT test. I don't have as much familiarity with that. But these mean the same thing. This is just called set notation. There's an even fancier way of saying set notation, but we won't get into that quite yet. All right. Oh man, we can't factor until it's in standard form. So I'm going to go ahead and add the 8. Now I can factor. All right. I know you're probably bored with these factoring problems. They're too easy for you. I know. It's okay. It's a good warm up. It's been a long summer, right? There, now we get a little nicer. Standard form, not there yet. So 2x squared minus x minus 3 equals 0. Now the reason this one's more challenging is because there's no way to get that 2 out of there. So we do have a 2 coefficient for the a value, which means it's not such a problem for the first term, but remember, when you multiply the outside and then you multiply the insides and you add them together, you need them to add up to a -1. Oh, hello. My a come from? Weird. X. You need them to add up to -1x, but we have to remember whoever's on this back end is going to get amplified by that 2 in the front. So we just have to kind of keep that in mind. So what if we called this a -3 and a +1? Let's see if that works out. So this outside arch is now a 2x, and this inside arch is a -3x, and that sure enough, when I add those together, I get -1. So this is where the puzzle part of it comes in, right? Some of us have a really tough time anticipating the puzzle, and we have to just kind of guess and figure it out. So when I solve this one, I get 3/2. And when I solve this one, I get -1. The worst thing you can do when you're factoring is just to give up and not try it because you think you're wrong, because that's not how we do math, people. All right, this next one, there's no common factor, so bummer. We do have a bit of a more challenging problem because we need to multiply that first one, that first arch by a 3. So 3x and x. And then also a bit of a bummer here, the last term's a 10, which has a few different factors, 5 and 2, 10 and 1. 10 and 1's a little extreme. I don't think we want to go there. Let's try 5 and 2. So what if I made this a -2, because that would give me a -6 out here, and then a +5. Would that do the trick? So when I solve my factors, this one gives me, oops, x equals a negative 5/3. And this one gives me x equals 2. Lovely. All right. Anything weird's coming up? Not yet. Oh, speak of our friend, the quadratic formula. You know, I feel like he kind of gets a bad rap some days. Some kids are like, I hate the quadratic formula because it's so hard to memorize. But now that we're in pre-calc, we're going to start making connections as to, like why this formula is what it is. And like I said, maybe in class I'll go through a proof of why the quadratic formula works. Essentially, it is what happens when you take a standard form quadratic, this guy right here, and you complete his square, and then you solve it through completing the square. It's really quite awesome. So the reason it's amazing, in my opinion, is because it always works. Sometimes it produces really beautiful solutions because of the quadratic. Sometimes it produces very crazy solutions because of the quadratic. And sometimes we'll find out later it produces complex solutions. So that's fun. We want exact answers. I don't want to see decimal answers because you guys are very crafty and you have like methods of using your graphing calculator to estimate answers. I'm not interested in that today. I want the exact answers. So this question, number 15, is already in standard form, so we're good there. The a value, b value, and c value, I can tell. So using quadratic formula, opposite of the b term, so positive 4, plus and minus square root, b squared. I can write negative 4 squared in parentheses, or I can just go, that's a 16. 16 minus 4 times a times c, all over 2 times a. Now, I don't mind simplification as you go along, and I know some of you will skip steps, but it's not a wise idea to skip lots of steps. So what I do is kind of off to the side of this radical, I draw another radical just for like my working memory, and I type in what we call the discriminant. Well, this one I don't think I have to type. 16 minus 4 is 12. Then I go, okay, self, how do we reduce the square root of 12? Because we do need exact, simplified, beautiful answers. So 4 plus and minus, 12 breaks into, remember, 4 times 3. So this is 2 square roots of 3 over 2. And then, oh, you think you're done, right? You're not. Because look at all my coefficients. 4, 2, 2. All of them are divisible by 2. So please do go ahead and divide all of those by a 2. So that's a 2 and a 1 and a 1, which leaves me with, I know this seems really lame, 2 plus and minus the square root of 3. Those are two solutions. They are irrational, which means they're not pretty if I tried to type them in my calculator. But that's what my teacher needs to see. All right, my next problem here. Same quadratic formula. It's already in standard form. You do want to notice also if the coefficients can all be divided by a common factor, just like when you do factoring, do it, because why would you want to work with bigger numbers if you don't have to? So this is not divisible by the same number. So opposite of b would be positive 6 plus and minus square root of, instead of saying negative 6 squared, let's just call that 36 minus 4 times a times c, all over 2 times a. Now, if you want a real thorough lesson on this, I got a beautiful Algebra 2 lesson somewhere out there in the world. It's color-coded, it's beautiful, it's pretty. You have to kind of decide what part of it you're messing up with, if it's something that's old, previous knowledge. So is it setting up the quadratic formula? Is it simplifying the radical? Is it reducing once it's simplified? That's what you have to kind of start pinpointing now at our upper awesome level of PreCalc. All right, on my calculator, this one, frankly, I might just type the discriminant in my calculator because, let's see, 20, 40, 76, which does reduce, if I'm correct. Yeah, okay. So 76 is divisible by 4. It's 4 times 19. So when I reduce that radical and this whole fraction here, we get x equals 6 plus and minus. This is now 2 square roots of 19 over 4. And then we have that same issue of, oh, I think I'm done, but not really, because 6 and 2 and 4, all those coefficients can be divided by 2. So I end up with 3 plus and minus. You don't have to write 1. That's weird. Square root of 19 over 2. So 2 very unattractive, irrational answers. That wasn't very nice of me. How judgy. Okay, this next one is not in standard form yet. So I'm going to rewrite it by subtracting the 6 over. I'm going to do a very bad math thing where you just do like a really large subtraction sign. Okay, don't do that. on your test. All right, so we have negative b, which is -1, sorry, -1, so +1. Plus and minus, -1 squared is 1, minus 4 times a times c, all over 2 times a. So same issue with before. I'm going to kind of off to the side look at this discriminant. 72, 1 plus 72, 73. That does not reduce, if I did it right. Yay! This is great news. I like when my quadratic formula does not reduce because it means less work. So 1 plus and minus square root of 73 all over 6. Coefficients don't reduce at all. So there's my two ugly answers. Oh, yes, this is a funny meme. I do love a good meme. This is an expression, and this is an expression. They're both polynomials. You cannot cancel pieces of polynomials like that. The only thing that crosses off and cancels are factors of multiplication problems. So we bring that up because a lot of kids feel like they should be able to reduce some stuff. Like right here, for instance, some kids think they're supposed to just say 2 over 4 reduces and then like walk away. That's not how things work. It has to be reduced all across the board or as a multiplication problem. Okay. B squared minus 4ac, the part that was underneath the square root symbol is called the discriminant, and he is very special. If that number inside the square root sign is a negative, we're going to have non-real numbers, okay, which means imaginary numbers. And I know when you learned this in Algebra 2, you were like, what? Yes, there are imaginary numbers. There's the complex number system. We'll come back to that like tomorrow, apparently. So if the discriminant is 0, however, there's only going to be one solution, okay? And think about that. You have your quadratic formula back here? Not there. Poor kitten. And after this plus or minus symbol, if you have the square root of 0, that's where the two different solutions arrive, is after the plus and minus. So if you're adding 0 and then subtracting 0, you're not getting a different solution. You're getting the same solution twice. So that makes sense. So what's the other option? Well, what if the discriminant is positive? That means that you have two real solutions. Okay? We've been finding two real solutions. Cat. So like this guy has two real solutions. They're gross, but they're real. Two real solutions, two real solutions. So they don't have to look pretty to be a real answer. The thing that makes them a real number is that they don't have a complex part, meaning there's no I in. So here, all they want us to do is calculate the discriminant to determine the number and types of solutions that we're going to have. This is also a way for you to tell if it's factorable, because if you end up with something where the square root, the discriminant is something nice, I say nice, but so like something that's a perfect square, like 36, 4, 16, 49. Those are all things that after you do the square root, it'll come out to a nice pretty number, meaning that your quadratic equation would have given you nice rational answers, indicating you could have factored it if given a choice. So if you're hemming and hawing over like, I don't know if I should try to factor this, you could quickly calculate the discriminant to determine that, if you want. Remember, 0 is a nice thing to square root as well. So let's take a look at this question, just calculating the discriminant. So b squared would be 25 minus 4 times a times c. So the value of the discriminant is something I should totally be able to do. 25 minus 8 is 17. Sometimes, I'll be honest, sometimes I don't even calculate the actual discriminant. I just go, that's totally positive. Either way, this is going to give me two real solutions. This next one is in standard form, so we're ready to set up 25, 5 squared, minus 4 times -3 times -10. This ends up being something very negative. Did I calculate it already? I don't know. Whatever, 25 minus 1/20. So negative something, which means I have 0 real solutions. Also indicating that we would have two imaginary solutions, which we will totally tackle tomorrow. And then here, b squared 16 minus 4 times a times c. 16 minus 16 is 0, which means when I do the square root of 0, I get plus and minus 0. I'm only going to get the same answer. I'm just going to get them twice. So there's one real solution. So discriminant's a neat little trick, right? Explore that. All right, I think I'm good. So that's our little reminder of how to solve quadratics algebraically, as long as they don't have complex solutions. We will talk about complex solutions. In fact, I think we're going to talk about them real soon. So look forward to that lesson. Remember, you can always go back to my Algebra 2 playlist if you need more thorough instruction on any of those methods.